Hey everyone, welcome to The Explainer. Today, we're diving straight into the 2026 landscape of industrial power electronics. Now, if you work around material handling, or AGVs, you already know there's a massive shift happening right now. But instead of just having another conversation about battery chemistry, we're actually going to look directly at the integrated systems powering them. Everything we're unpacking today really anchors on one core idea: the intelligence behind the plug. It's kind of like going from an old flip phone to a modern smartphone. We're way past just getting power into a vehicle. Now, it's all about how smart, efficient, and integrated that power delivery actually is with the rest of your operation. So, here's our roadmap. We're going to track this shift starting from the 2026 fleet inflection point, break down the all-in-one architecture, see how these systems survive harsh industrial realities, explore V2X energy assets, and wrap up by benchmarking a real-world standard. Let's get into it. Starting off with Section 1, the 2026 fleet inflection point. You know, a lot of the industry right now is totally fixated on swapping out old lead-acid batteries for lithium-ion LFP, and honestly, they're treating it almost like a simple AA battery swap. But the true enabler of fleet efficiency is actually the integrated intelligence managing that power. Think about it. If you upgrade the battery without upgrading the brain, you're essentially leaving a tremendous amount of operational efficiency right there on the table. Which brings us right into Section 2, the all-in-one system architecture. Think about the traditional modular mess we're used to seeing. Separate boxes, extra wiring, and just way too many points of failure. The 2026 standard cleans this up entirely into what we call an integrated hub. We're talking about combining a 6.6 kilowatt onboard charger with a 2 kilowatt DC to DC converter, all packed into a single, streamlined housing. And the absolutely crucial takeaway here is that 30% figure. Consolidating everything strips away a massive 30% of the system mass and cabling. For a fleet manager or a mechanical engineer, that is a real game changer. Less weight means less energy spent just moving the vehicle, which frees up physical space for much bigger payload capacities or tighter turning radiuses in those super narrow warehouse aisles. So, how do they actually pull off this compact design without the system just literally melting down? Well, engineers rely on something called LLC resonant topology. Now, I know that sounds like a super dense academic term, but actually, just think of it as a highly tuned shock absorber for electricity. It drastically smooths out the power flow, which means you waste far less energy as heat during the conversion process. And because less power is lost to heat, these modern systems hit an incredible peak conversion efficiency of 94% or higher. In a massive industrial warehouse where electricity costs are one of the biggest line items on the budget, being able to claw back every single percentage point of wasted power, that directly, measurably improves your bottom line and the long-term ROI of the entire fleet. But of course, high tech is totally useless if it breaks the second it hits the floor. Let's look at Section 3, surviving harsh industrial realities. Let's be real. Industrial vehicles do not get sick days. They face brutal conditions every single day. We're talking heavy dust infiltration, high-pressure washing, extreme mechanical vibration from absolutely terrible factory floors, and major outdoor temperature swings. Your standard consumer electronics wouldn't last an hour out there before failing completely. So the defense against this chaos is a two-pronged approach. First, you absolutely need an IP67 rating, which makes the hardware a literal, waterproof, and dust-proof fortress. But physical armor just isn't enough anymore. Inside, it uses a communication protocol called CAN bus 2.0b. Think of this as a flawless, continuous digital handshake between the charger and the battery, making sure the battery's health is strictly monitored and protected no matter what's going on outside. All right, moving to Section 4, V2X, or Vehicles as Energy Assets. This is where we transition from just surviving the grid to actually exploiting it. Let me ask you a question. What if the hours your vehicles spend just sitting idle could actually generate revenue, or at least heavily offset your facility costs? Historically, an idle forklift is nothing but a sunk cost, right? But in the 2026 landscape, that whole paradigm flips completely on its head. By enabling bidirectional energy flow, your fleet literally becomes a mobile energy storage unit. It's a pretty straightforward setup. First, you integrate the bidirectional V2X system. Second, you unlock what's called peak shaving, meaning you charge your vehicles at night when electricity is dirt cheap, and then use their batteries to help power your factory during those super expensive peak demand hours. Finally, they can actually backfeed power to stabilize the smart factory grid. You are effectively turning a dormant vehicle into an active financial asset. Okay, to see how this all looks in practice, we arrive at our final section, benchmarking the AODI standard, using their portfolio as our real-world case study. Looking closely at their timeline, AODI has a serious 16-year trajectory in this space. Founded back in 2010, they rolled out liquid-cooled chargers by 2014, and recently expanded globally with a branch in Mexico by 2023. This kind of history gives us a really useful lens for understanding the deep manufacturing maturity you actually need to meet these 2026 V2X smart grid standards at scale. And when you're benchmarking industrial power, the paperwork matters just as much as the hardware. You have to have validations like IATF 16949 for automotive quality management and ISO 14001 for environmental management. These are not just alphabet soup. They are the strict gatekeepers, proving a supply chain is truly robust enough for global, heavy-duty deployment. Because scaling this technology requires massive physical infrastructure, MODI has scaled up to a capacity of 30,000 units per month across 4 automated production lines. 30,000 a month. That massive number really illustrates the sheer volume of integrated systems the global market is demanding right now, as it desperately transitions away from outdated tech. And that capacity has naturally led to deep integration right into Western logistics infrastructure. Securing Tier 1 OEM status means these power electronics have been thoroughly vetted and embedded by recognizable industry giants: Toyota, JLG, Skyjack. It perfectly shows just how interconnected the global standard for industrial equipment has actually become. So as we wrap things up today, if you only take one thing away from this explainer, let it be this. The transition to LFP is a complete system-level upgrade. If an operation merely swaps out the battery chemistry but totally ignores the power electronics, the integrated hub, and those bidirectional capabilities, they are missing the most important part of the entire equation. I'll leave you with this final, provocative thought to take back to your own operations. Is your fleet truly ready to bridge the gap between high-performance battery cells and the smart grid? Are you absolutely prepared for the intelligence behind the plug? Think about it. Thanks so much for exploring this with me today, and I'll catch you on the next explainer.